And then this talk will be concluded, will be ended with some concluding remarks. Okay, first, let me address some key challenges and opportunities beyond 5G. Arguably, the most innovative idea of the 5G system design could be supporting distinct service type, utilizing different service links. In other words, EMBB, URC, and MMTC. But however, in the next upcoming systems and applications, people are expecting and contemplating a bit more challenging applications consuming the type of the traffic that is a mixture of such distinct services. As an example, let's imagine a VR user that is in a virtual space who is watching a 360-degree high-resolution video clip while playing with Rubik's Cube by hands. It means that this user consumes URS-like service type service, while at the same time consuming tactile, in other words, URS-like service. Means that and under the current service breakdown in 5G, supporting this type of mixture user is very difficult and negating the effectiveness of the breakdown. On the other hand, arguably the most challenging service type out of these three could be URC. But even beyond 5G, people are expecting that the service requirement for the next generation URC will be even more stringent. For example, the reliability will be targeting at achieving 99.9999 reliability and even sub-millisecond latency. And given the current architecture and limited radio resources, it will be very difficult to support. In reality, it could be impossible to support such a challenging applications at the same time, at scale. So this calls for a disruptive and an innovative solution. One may claim that, as we've done before, at the transition from the 4G to 5G, we can do the same thing for the transition from the 5G to 6G. In other words, let's use more bandwidth at higher frequency, like terahertz bandwidth. But unfortunately, there may not be a sustainable solution. As an example, as claimed by this interesting paper at the bottom, it calculates the surface temperature of the given form factor, the smartphone form factor. Then it considers the maximum limit of the temperature, surface temperature of such a form factor, given the energy entropy low. Then the maximum temperature should be limited by 45 degrees Celsius. Otherwise, it will be too hot to hold. So given the more slow and given the level of the circuitry advancements, it calculates that to support 100 gigabps rates, regardless of the types of frequency bandwidth and many more, just to support that rate for the given low-end circuitry, 100 gigabps could be the maximum limit to satisfy the temperature condition for the given form factor. In other words, unless we consider even bigger form factor, it will be difficult to even hold it. So terahertz, it is questionable to utilize terahertz for such a versatile application in our everyday life. So in this respect, utilizing machine learning has attracted many attention in both academia and in industry. As an example, in this Next Year Alliance's report reported to the US government, it claims that the AI-enabled advanced network and services designs could be the key enabler for the next generation services. So with such machine learning aided design, the benefits are exemplified as follows. One can predict rare and emergent events utilizing machine learning, and one can for better prediction, one can also use not only the typical RF signal modality data, but also one can combine them with the non-RF modalities such as vision, speech, haptic, and many more, natural language. And then thereby we can understand the environmental dynamics more explicitly and clearly and accurately. As an example, the channel distribution variabilities, and what else? Channel distribution coherence time, coherence interval, and even contrast state dynamics, and many more. And finally, we can thereby reflect the effectiveness of the communication for a given service use cases, and in other words, the task. Those are the benefits. Achieving those benefits can be summarized by learning to communicate. In other words, machine learning for communication. But at this point, we have so far implicitly postulates that machine learning is perfect. In other words, we have an ideally trained machine learning model. Machine learning is data-driven, so it is not always true. So the key bottleneck in reality would be the lack of data sample at a single location. It means that we need to communicate the data sample, incurring the communication overhead straightforwardly. But unfortunately, often those samples are privacy sensitive, like such as our health records and location history, and not to mention the limited resources and computing resources. And these addressing these bottlenecks could be summarized by the research direction of communicating for machine learning, communicate to learn, communication. In other words, communication for machine learning, and this is also summarized by machine learning at the network edge machine learning. And federated learning is the first of its kind, and that has been selected as one of the 3 key next generation artificial intelligence frameworks by Forbes late last year. And in both academia and industry, people are highly recently very interested in advancing such edge machine learning from the E community and CS community, as well as the many industry initiatives such as Google, IEEE Comsci, Baidu, Baidu, and what else? WeBank, and many more. And to begin with, to go into more detail, let me first summarize the key problem of the edge machine learning. That is summarized by this Finnish cartoon. As you may know or not, Finnish people are very famous for their shyness. So in this cartoon, the boy on the right hand side wearing the blue hat, he wants to take a free food sample in a supermarket corner, but he doesn't want to chat with the salesperson. So likewise, in the edge ML scenario, each worker wants to take the high quality machine learning trained model, but they do not want to share their raw data. In other words, to obtain a high quality medical disease diagnosis model, they want to obtain such models, but they do not want to reveal their say Apple Watch or Galaxy Watch health records. And likewise, they want to obtain a high quality, highly accurate navigation route prediction, but they do not want to reveal their location history over time. And last but not least, they want to obtain the future energy prediction for smart metering, but they do not want to share their everyday energy consumption. So to address such a edge ML problem, federated learning is a frame. Federated learning exchanges the model parameter without revealing the raw data. So here's a summary of the federated learning operations. Let's look at the figure on the right-hand side. This is a standard system model where we consider a parameter server that is associated with multiple remote workers, and each worker is associated with its local data set and local model, and utilizing only its local data set, it trains its local model with multiple iterations, and at a given regular interval, the local worker uploads the local model updates to the parameter server, and the parameter server aggregates such local models, construct a global model by taking the average, and then the constructed global model is downloaded by each worker. And for the next round, the local worker replace its previously calculated local model with the downloaded global model and keep iterating this procedure. So from the optimization perspective, this operation can be summarized by, from the local worker's perspective, can be summarized by minimizing its own loss function subject to a local model replacement constraint. In other words, global model can be regarded as a regularizer from each local worker's perspective. And the aforementioned algorithm has been named as federated averaging algorithm. That is the standard vanilla federated learning algorithm. And then there are many advanced algorithms in addition to federated averaging, such as federated stochastic gradient is a federated SGG that exchanges the gradient instead of the model weights, and federated SVRG that tries to that considers an anchor model that enables to reduce the variance of the gradients. But regardless, those algorithms can still be summarized by the same principle, injecting the global model as a regularizer at a given interval. One key challenge of the federated learning is the environmental challenge that is that comes from the nature of the locally generated, locally stored data samples. They may not follow the same distribution across different workers. In other words, the entire data distribution could be non-IID. Under such non-IID data training samples, under various data, say public data set, MNIST and Cypher10, we can see that there exists a huge accuracy gap in between the IID case and its counterpart non-IID case. So to address such a non-IID problem is one key challenge of federated learning. And here, from the optimization perspective, here's a brief history of the federated learning. The root comes from the gradient descent proposed by Cauchy in 1947. It utilized a full batch per each computing iteration. And then that has been extended to stochastic version, SGD, and which is also called as a Robinson-Monroe algorithm that it was proposed in 1951. It utilized a randomly selected single sample per each computing iteration. And integrating the gradient descent and stochastic gradient descent, the mini-batch SGD has been proposed in which utilize one mini batch that is smaller than the full batch per each computing iteration. Up until now, we have considered standalone machine learning operations. Extending this to the parallel version, distributed version, distributed stochastic gradient descent has been proposed, in which the communication has been performed per each computing iteration. And federated learning is a variant of distributed SGD, in which the communication happens at a regular interval. In other words, communication is periodic. So that is summarized as a federated averaging algorithm or federated SGD and many more. Federated averaging and federated SGD have been proposed by Brendan McMahon at Google in 2017, and then later people have realized that and rediscovered that it coincides with the previously proposed optimization algorithm, local SGD, by Mangasarian in 1995. That is the same as the federated averaging algorithm. So in the algorithmic front, federated learning may not be a novel idea, but still the federated learning is a novel framework or a paradigm for in terms of suggesting to consider such a user database training and under even heterogeneous settings and many more. So in this respect, recently, local SGD has been revisited, and the convergence analysis has been performed under various settings, such as IID data set, data distribution, non-IID data distribution, heterogeneous computing rates, and what else? A fraction of the participation, and many more. But nevertheless, at this point, we need to consider the fundamental limitation of federated learning. That is, federated learning is based on exchanging model parameters. So if the model size is very large, such as then the communication payload is increasing proportionally with the model size. See, as an example, in this inception version 4 model that consists of 42 million parameters that correspond to 44 gigabytes. Means that per each communication round, each worker needs to send and receive such a large communication payload that is not realistic even under 60 systems. So this calls for mandating to develop a totally novel solution. One possible idea is to exchange model outputs instead of the model parameters. That is epitomized as Federated distillation we have proposed. And Federated distillation is based in knowledge distillation, an algorithm that is originally proposed for compressing a model. In knowledge distillation, it considers two models: a pre-trained teacher model and an empty student model. And the goal is to train this empty student model by utilizing this pre-trained teacher model's prediction capability, inference capability. To this end, let's feed the same sample to both models, student and teacher, and then both models return their own outputs. And we know that the teacher's output is more reliable compared to the student's output. So measuring the output gap between the student and teacher, let's distort the student's own weight update calculation with the amount that is being proportional to the gap between the student and teacher's output. That is called distillation regularization. And to utilize this knowledge distillation for distributed learning, it is not straightforward because it postulates a pre-trained teacher model. The goal of distributed learning is to obtain such a trained model. So assuming the trained model a priori is not a realistic scenario. To overcome this problem, we have revisited a variant of knowledge distillation that is called co-distillation. In co-distillation, the key idea is as follows. The existence of the need for pre-trained teacher model in knowledge distillation is to provide at least a bit more reliable output compared to an empty student model. And the fact is it motivates by the fact that an ensemble of the ensemble output of the multiple model is often more reliable compared to one single neural network model's output. So so utilizing this intuition, in co-distillation, each student sees all the ensemble of all other models' output as its teacher. So physically, there exists no pre-trained teacher, while each student sees all the others' ensemble as a teacher in real time, in parallel. So without assuming any pre-trained teacher model, co-distillation is able to train multiple only student model in parallel. So this is quite close to distributed learning scenario, but still the one key limitation is that to run the knowledge distillation, we need to feed the same samples to both student and teacher. Otherwise, measuring their output gap may be useless. But in this co-distillation setting, it means that feeding the same sample to all the devices per each computing iteration that incurs huge communication overhead while exposing too much raw data privacy. So to overcome this problem, we have proposed Federated distillation. So the key idea is let's not utilize a sample by sample correlation, but instead we can utilize a label by label correlation. So here's the idea. Here's the operation. Consider each one single local device, and during its local iteration, it stores and saves all the outputs per each label. Here, a blue label per blue label and per yellow label. And then the average, the locally average output that is called logit, the locally average logit is uploaded at a regular interval, is uploaded to the parameter server. And the parameter server takes an average of the uploaded local logit across multiple workers per each label still. So the global, so thereby the server has constructed the global average logit per different labels. Then the global average logit per label is downloaded by each worker. And in the next round of the local training, if the student models feeding data sample correspond to this blue label, then the downloaded blue label corresponding global average logic can be regarded as teacher's output. Otherwise, the yellow, if the feeding sample correspond to the yellow label, then yellow downloaded average global logic is regarded as a teacher's knowledge. In so doing, we can perform the an approximate version of the code distillation without exchanging the raw data samples. So let's compare the federated distillation and federated learning in terms of accuracy and computation efficiency. So under the MNIST data set, as shown by the figure on the left-hand side, federated distillation can achieve around 10,000 times less communication overhead until convergence, but at the cost of, unfortunately, compromising some accuracy. So at this point, we can recall the fact that in wireless communication settings, it is quite common that the uplink capacity is quite much more restricted compared to the downlink counterpart. So utilizing this aspect, we can combine federated learning and federated distillation as follows. In the uplink, we can utilize federated distillation for minimizing the communication payload size, while in the downlink, we can download the model parameters as done in federated learning for maximizing the accuracy. And in between the uploaded model output parameters and the model uploaded model outputs and the to be downloaded model parameters, we need to convert we need a conversion from the outputs to the model parameters. That can be done by running knowledge distillation at the parameter server. So as you can see in the systematic figure on the right-hand side, the green curve that corresponds to the proposed algorithm outperforms the both vanilla federated learning and federated distillation algorithm under a asymmetry uplink and downlink channel. And let's consider let's talk about the convergence property of the federated distillation. Is it whether it converges or not is a bit more questionable compared to federated learning because federated learning is relying on fundamentally relying on gradient descent, and whose convergence property is well known. But on the other hand, federated distillation is rooted in knowledge distillation, whose convergence property is hasn't been improved until late last year. So very recently, knowledge distillation has been the convergence of the knowledge distillation has been improved by utilizing a very recently proposed analytic tool, neural network kernel. Neural network kernel is an asymptotic. Yeah, neural network kernel is an asymptotic analytic tool in the sense that it considers an infinitely wide neural network layer, and we by assuming such a infinitely okay, so with assuming such a infinitely long width of each layer, conceptually we can say that the output of the layers are governed by the well-known central limit theorem. So as a result, the output of the neural network is governed by, is only dependent on the input of the neural network. In other words, we can analyze the output dynamics of the neural network you only using the input in a deterministic way. So here, to this end, we consider the knowledge distillation, the student's optimism problem under knowledge distillation. And when the number of iteration t goes to infinity, then the student's output ft as t goes to infinity is converging to the expression in the middle on the right hand side. And then here the y represents the ground truth label, and then the term after the plus sign represents the pre-trained teacher's output. So if the pre-trained teacher's output converges to the ground truth output, in other words, with the ideally trained teacher model, the student's asymptotic output f infinity is also converging to the ground truth output y, right? otherwise, the student's asymptotic output is limited by the level of the teacher's training. On the other hand, to prove the convergence of the federated distillation, let's revisit the co-distillation. Co-distillation can be regarded as the upper bound performance of the federated distillation, in a sense that the co-distillation, each worker observed the same data sample and measuring the output gap. So that could be the most exact one. On the other hand, in federated distillation, the output data sample could be different, while only their labels are the same. So in this respect, measuring the gap while feeding the same data sample, in other words, co-distillation performance can be regarded as the upper bound performance of the federated distillation. And co-distillation, we can prove the co-distillation's asymptotic convergence utilizing the same neural network, the neurotangent convolutional framework, in which when we consider the infinite number of communication round R, then interestingly, the student's output F1R, randomly selected the first student's output F1R converges to the ground truth label Y, regardless of even without considering any pre-trained model. In other words, starting from the scratch, while keeping improving each student's model, co-distillation can achieve the best possible accuracy. So that could be a surprising result. And here we can recall the accuracy gap between federated learning and federated distillation. In fact, comparing these promising and positive asymptotic analytic upper bound results, we can see that it is quite difficult to understand why federated distillation performance was too poor compared to the federated learning in the previous slide. So let's consider let's seek for what could be what are the possible reasons. One key reason could be this one. Compared to federated learning, where each worker exchanges the latest the freshest trained model right before communication round at checkpoint. Federated distillation at each communication round at checkpoint, communication checkpoint, each worker exchanges locally averaged the output. It means that some outputs included in that locally average, time average output would be even outdated. It does not reflect the freshest model's inference capability. So to fix this problem, we can consider this codebook-based very simple solution. In other words, let's consider the same exam proxy data set across all the workers. So in other words, during the local training, each worker is relying on its local data set, but right before the communication checkpoint, they do the test with the same test exam questions. In other words, the proxy data set. By feeding the same data set at each worker, we can measure their outputs more accurately while reflecting each model's freshest model prediction capability. So with this simple fix, recent follow-up works by King's College, Kyoto University, and Fraunhofer in Germany have achieved a variant of federated distillation algorithm have achieved even higher performance higher accuracy compared to federated learning. And another possible limitation of federated distillation is that up until now, we have implicitly assumed that classification task, because federated distillation relies on the label by label synchronization. Label exists in classification problem, but it does not in say regression problem and even reinforcement learning problem. So here, let me give you an example of reinforcement learning. Actually, the same principle used in federated distillation can easily be utilized in reinforcement learning scenarios. The key is just utilize some correlation of the input rather than utilizing the raw data sample. So it doesn't have to be the exact label, but in the context of reinforcement learning, such kind of sample grouping or clustering could be possible by focusing on the fact that the neighboring states, in this cart pole example, the cart angle, the neighboring angle could be approximated as the center value, say minus 45 degrees and the plus 45 degrees. So any values in between those range can be approximated by these representative values, and those representative values can be corresponding to the label in the classification test. So by applying the same principle, we have also proposed the reverse learning version of the federated distillation that is called federated reverse distillation, and that also outperforms the case of this standalone operations. And next, let's consider another possibility of the computation efficient digital learning framework, that is split learning, that exchanges the hidden activations and hidden layers gradient instead of exchanging the model parameters as well. So let's compare the federated learning and split learning architectures. So federated learning, from the perspective of the parallel computing, federated learning can be categorized as the data split architecture, where there exists one single server that is communicating with multiple workers who store different data sets. Data sets are split. On the other hand, split learning considers under data split, each worker should store the same model architecture. Only the local data sets are different. On the other hand, in split learning, data sets are different, but also the local models are also different in a sense that one local model is split into, as an example, two parts, and the upper part is stored at the server side that is shared by multiple workers, and the lower part is stored at the local worker side, and these lower part of the model could be different for different workers. In other words, one single model is split into multiple parts, while worker stores and utilize different data sets. In other words, split learning is a combination of data split and model split. And let's compare the communication efficiency of the federated learning and split learning. In federated learning, the uplink payload is the entire model parameters, and the downlink is also the entire model, the global model parameters. The communication interval is periodic. On the other hand, in split learning, the uploading the uplink payload is the one single layer, the cut layer activation in the forward propagation in the uplink. On the other hand, the downlink, in the downlink, the payload is the single layers gradient back propagated from the server to each worker. And the communication interval in the standard vanilla split learning algorithm, the communication interval is per each iteration. So compared to federated learning and split learning, whether the split learning is more communication efficient or not is not a trivial question. But interestingly, recent work, prior works, have compared the communication efficiency of the federated learning and split learning, and the conclusion is follows. Split learning achieves a higher accuracy with a small payload size and even faster convergence. It means that split learning is a free lunch. It does not lose any useful properties. But here, these results is holds for in the context of accumulated data bits until convergence. So if you go beyond counting bits, answering the question of the communication efficiency of split learning is not a trivial. For example, what about the impact of the stragglers, and what about the latency under intermediate channel fluctuations over wireless links? So to answer this question, let me ask three detailed questions and provide an answer. First, the first question is, can the split learning control the number of stragglers? So before going into the detail, let's first consider the default architecture of the split learning, in which the one parameter server is associated with is to be associated with multiple workers, but their association is in a sequential way. It means that it starts with the first worker, and then utilize the entire data set, and then the next worker is associated with the parameter server, and the next connection. The third worker is connected to the parameter, and so forth. Means that the operation is sequential, and the communication is performed per each data sample. But when we know that it's quite trivial that this is not a communication efficient way, and we can consider not sequential, but parallel version of the split learning. One possible way is to concatenate multiple outputs of the workers as the input of the parameter server's upper part of the layer. In this case, we can consider each worker is feeding the data sample, different data sample, but while synchronizing their labels. In other words, feeding different cat images, but feeding different images, but they are still cat images. But with this concatenation, one key problem is that neural network architecture is not flexible. But channel quality vary over time. Channel qualities vary over time. So in the worst case, the server should wait until the last straggler arrives at the server. It may incur infinite communication latency. So to fix this problem, one simple solution is to taking an average. In other words, introducing a pooling, say average pooling layer at the server side. So regardless of the number of workers, multiple workers' outputs are averaged right before the input of the parameter server's a fraction of the upper part of the model, and then thereby we can control the number of straggler simply by utilizing the average pooling layer. This idea was motivated by the so-called manifold mix-up idea that utilize in which the multiple neural network models hidden layers are averaged with the ratio lambda. And when we consider this lambda is set as uniformly set as a uniform value, then that coincides with introducing the average pooling layer. And the performance of manifold mix-up has been heuristically proven that it often outperforms the standard alone training. And another background is that so far, on the right-hand side, in this scenario, we have considered, say, horizontal partitioning, in which each worker feeds a data sample with the same data label, but on the other end, there exists the counterpart, vertical partitioning. In other words, instead of synchronizing the label, but instead we can synchronize the key feature while feeding different entity. Under this vertical partitioning, in recent works, very similar idea. Utilizing averaging pooling is also effective. So we, in other words, what we have done is to apply the same technique, not under vertical partitioning, but under horizontal partitioning. And utilizing this, as we can see in the figure on the left-hand side, parallel split learning under the concatenation, the solid green curve, is almost the same as the parallel split learning under with average pooling. It means that average pooling is a free lunch. And we can see the parallel split learning in both cases outperforms federated learning in terms of the computer speed and accuracy, and outperforms federated distribution in terms of the accuracy. And second question is, can the communication period of split learning be communication interval of the split learning periodic? That's the second question. And then that is also simply doable by increasing the batch size. In other words, when we consider when we increase the batch size, it means that each worker feeds multiple data samples, and then accordingly, multiple data samples corresponding hidden representation are fed into the upper layer through omnic communication, And the solver, with those multiple samples, calculate one single loss function, and then accordingly, one single gradient is back propagated propagated back to each worker. So in other words, a batch size increase means that packet aggregation. So in split learning, we can see that it exchanges the communication payload is one single cut layers representation. So its payload size could be perhaps too small. Then we know that it may lie in the short packet regime where there exists a short packet data rate loss that diminishes when we increase the packet length. So here, batch size increase is identical to merging, integrating multiple data sample, multiple packets. So we can further reduce the short packet data rate loss while increasing the communication interval. So in our preliminary result, when we increase the batch size, we have observed that under non-ID MD data set, we have observed that the latency, the communication latency decreases, but at the same time, the test accuracy also decreases, means that there is a trade-off between the communication interval, the communication efficiency and accuracy with respect to the batch size control. But in reality, there exists many techniques to utilize large batch training. So by applying such advanced techniques, we believe that there exists a win-win strategy. In other words, batch size increase can also increase accuracy, or without losing any accuracy, we can control that, we can increase the communication interval as we wish. The last question, can split learning mitigate straggler? Probably this is the most fundamental and crucial problem. That is given as follows. In split learning, in federated learning, let's consider a straggler. In other words, that failed to participate in one given the previous communication round. So for a straggler, even it couldn't contribute to construct the global model in the previous round, for the next round, it is always beneficial to download the freshest global model, because the local model is simply replaced with the downloaded global model, right? But on the other hand, in split learning, let's consider the same straggler. They failed to contribute to the constructing the omni communication in the previous round. And let's consider the next round. Is it beneficial for receiving the global the global updates or not? Actually, surprisingly, it is even not feasible. The reason is follows. In split learning, the downlink information is the gradient. And the gradient, the definition of the gradient is the loss function, and the gradient is taken with respect to the weight. But in the split learning architecture, the forward link failure straggler means that it is identical to the weight connection was dropped in the previous round. So in other words, we cannot even calculate the gradient because there exists no weight corresponding to such a straggler. One possible naive solution is to download instead the average gradient. Average is taken for all the other workers that are non-straggler workers, and as shown in the simulation on the left-hand side, we have seen that downloading such average gradient is not even beneficial. It even decrease the accuracy, particularly when the number of straggler is large. As an example, when the number of straggler is 4, if the number of the optimal number of average gradient received straggler is 0, in other words, average gradient downloading is harmful for stragglers. So to fix this problem, we have proposed not to a novel algorithm that does not rely on the gradient backpropagation, but instead the model output backpropagation, motivated by the knowledge decision as well. So here, the operation is as follows. Multiple workers are observing the data samples, and the data samples are fed forwarded into the next layer through, say, with or without the pooling layer. And accordingly, the output is calculated at the server side, the last layer of the server side. And then let's broadcast the output of this server's last layer. And then with this broadcasted, downloaded global output, we can consider, we can measure the output gap between the server's last layer output and the student's last layer output. And by measuring this gap, we can locally train this each worker, regardless of whether it was regulated the previous round or not. So this idea was originally motivated by this local parallel training recently submitted in to iClear by Google and GraphQuar. And in this work, they have considered a single neural network model is split into multiple chunks, and then on the left-hand side, consider the lower chunk is locally trained with its local loss, and then the output, the generated outputs are fed into the next layer, and then next layer without backpropagation can be locally trained using its own local loss. And iterating this operation, one can train the entire neural network. And here, interpreting this figure from a bit different perspective, we can interpret that the lower chunk can be regarded as student, and the combination of the lower and upper segments, in other words, the entire model can be regarded as teacher. In this case, both student and teacher model have observed the same data samples. Then we can do the knowledge distillation. And in our preliminary result, with a single worker case on the Cypher 100 data set and a variant of VG16 neural network model, we have observed that the previously the aforementioned ideas, student model outperforms the standalone student model. So here's a conclusion. Beyond 5G, system communication designs call for communication efficient edge machine learning frameworks. And federated learning is the first of its kind and is a promising solution, of course, but yet it is ill-suited for coping with, dealing with large-size neural network models. Imagine not only the cell phones or small IoT devices, but let's consider, when we consider vehicles or satellites and with a larger form factor that's capable of running a bit higher, large size or high capability models, then we will be facing the same problem. Then for handling such large models, federated distillation is more suitable solution, but at the cost of compromising its accuracy. And parallel split learning is suitable for both large size model while without compromising any accuracy, but is vulnerable to wireless communication channel variabilities. So to resolve these problems, we have proposed and introduced several possible ideas to improve the communication efficiency of such HML frameworks. And that requires to co-design discrete learning and model architecture and communication techniques. And I believe that this is a new research direction, still in infancy, and there are still many research problems we need to solve together. That's the end of this talk. Thank you.